In this video, we are going to learn how to determine the RNS configuration of organic compounds. So for example, let's consider this molecule. Are there chiral compounds? Are there chiral centers in this molecule? You can only identify a chiral center if the carbon is bonded to 4 different groups. So in this case, we have a proton here. Here is a CH3 and here is a CH3. And because we have 2 groups on the carbon that are equal, then this carbon is not a chiral center. Let's come to this side. There is also a proton here. And then there is another one here. So because we also have 2 groups that are the same on this carbon, then this carbon is not also a chiral center. A molecule that does not have a chiral center is an optically inactive molecule, except for some few exceptions. Let's also consider this molecule. Does this molecule has a chiral center? This carbon is bonded to by a CH3 here, and another CH3 here, and another CH3 here. So because we have at least 2 groups that are the same, then it means that this carbon is not a chiral center. The way we determine whether groups are equal or not is by their molar mass. So we use molar mass to differentiate the various groups that are bonded to the carbon. Let's consider this molecule as well. And here is a chlorine. Is there any chiral center here? If we consider this part of the molecule, there is a proton here. So we have a proton here. And then we also have another proton here. So because we have 2 groups that are the same on this carbon, it means that this carbon is not a chiral center. And for this carbon too, we have a proton here, and there is another one here. So another 2 groups that are equal. So this carbon is not also a chiral center. And let's consider this carbon too. We also have 2 groups. There is a proton here, and then there is another one here. So because we also have these 2 groups on this carbon that are the same, then it means that all these carbons are not chiral centers. So this molecule is an achiral molecule. This one too is also achiral. And then this one too is also a chiral molecule. Now let's consider this molecule. Let's start from this place. Is that a chiral center? You can see that there is a CH3 here, there is a proton here, there is a chlorine group here, and then there is an ethyl group, C2H5. So you can see that we have 4 different groups that are bonded to this carbon, and for that matter, this carbon is a chiral center. I use asterisk to indicate chiral centers. Now let's come to this carbon. This carbon has a proton here, and it also has another proton here. And because we have 2 groups that are the same on this carbon is not a chiral center. So this molecule has got only 1 chiral center, and therefore it is a chiral molecule. And because it's a chiral molecule, it is also optically active and will rotate plane polarized light. The total number of stereoisomers that a molecule can have is 2 exponent n, where n is the total number of chiral centers that are in that molecule. Consider this substituent. We are supposed to arrange the substituents in decreasing order of priority. So when we are assigning positions, which ones will come first and which ones will come last? Priority is given with reference to the molar mass. So you see that here's a carbon, here's an oxygen, this is also a carbon. The molar mass of oxygen is greater than carbon, and therefore OH will come first. When you come here, this is a CH3 and this is a CH2. So from the carbon, we go to 3 protons. However, from this carbon, we go to 2 protons and another carbon. So this group will have a higher molar mass than this group, and therefore that one will come second. And then the last CH2, Cl will come second, and then the last one will be the CH3. So this is in decreasing order of priority. So this is a decreasing order. Let's also consider this arrangement. Which ones come first and which of the groups comes last? Now, when you see a triple bond, you are supposed to look at it in terms of each of the carbons is bonded to 3 nitrogens. So in this case, this one will look like this. This carbon is bonded to 1 nitrogen, and then it is also bonded to another nitrogen and another nitrogen. And in the same fashion, each nitrogen is bonded to 3 carbons. So this one is bonded to 1 carbon, another carbon, and another carbon. And so you can see that in this situation, there are 3 carbons here. And in this situation, there are 2 carbons here because it's a double bond. If it is a double bond, then it's going to look like carbon bonded to 1 carbon, bonded to another carbon. And then this carbon is also bonded to 2 of this carbon, so C and C, then the H3 will come. So we will give precedence to a triple bond before a double bond. And therefore, if you look through, they are all carbon, starting with carbons. But anytime you have a triple bond, the triple bond will come first. And therefore, C triple bond N comes first. Then the next one is the double bond. So this double bond will come next. CH2. Then the chlorine group, here is a CH2Cl. But here is a carbon bonded to 2 protons and then a nitrogen. Chlorine has a larger molar mass than a nitrogen, and therefore CH2Cl comes next. And the last one is CH2NH. So this is also decreasing order. Consider this arrangement. Each of them starts with a carbon, but in 3 of them, these 3, the carbon is bonded to a double bond to oxygen. Here is a single bond to oxygen. We always give precedence to the double bond over a single bond and a triple bond over a double bond. However, if you come to the next groups, this carbon is bonded to a CH, a carbon first. This one is bonded to an oxygen. This one is bonded to a nitrogen. An oxygen has a higher molar mass than a nitrogen, and a nitrogen has a higher molar mass than a carbon. And therefore, this molecule will come first. So the first one is going to be C double bonded to oxygen, single bonded to an oxygen, and CH3. And the next group is the one containing the nitrogen, which is carbon doubly bonded to an oxygen, then to a NH2 group. Then the next one is this one, which is carbon doubly bonded to an oxygen, a CH3 group. And then this is the last one, and that is carbon singly bonded to an oxygen, OH group, and then an NH2 group. So this is also a decreasing order of priority. Having understood this, let's then go ahead and determine the R and S configuration of an organic molecule. Let's consider this molecule. Is this molecule having an R configuration or an S configuration? The R and S shows where the molecule will rotate in plane polarized light, whether in the clockwise or anti-clockwise direction. But as to whether it will rotate light in the clockwise direction or the anti-clockwise direction is determined only by experiment. Now, if you are given a configuration like this, the first thing is to determine the positions or the ranking of the various groups that are bonded to the carbon. In this case, a bromo group has a higher molar mass than a chlorine group, and a chlorine has a higher molar mass than a carbon, and a carbon has a higher molar mass than a proton. So the bromine group becomes number 1, the chlorine group is number 2, and then the CH3 is number 3, and then the proton is number 4. Now, what you must ensure is that the least group must always be pointing away from you. In other words, the least group must be on the dash bond, because the dash bond is the bond that indicates the groups that is pointing away from you. And so in this case, you can see that the proton, which is number 4, is pointing away. So what we do is that you cover the group that is pointing away, and then you determine the direction. So here's 1, 2, 3. 1, 2, 3 in the clockwise direction, because we have covered the group that is facing away from us. And for that reason, this is an R configuration. So what is the configuration of this molecule? The first thing is to determine the priority. Now the D stands for a deuterium. And we know that fluorine has a higher molar mass than a carbon, so fluorine becomes 1. Nonetheless, this is a CH3 and this is a CH2C. So in this CH3, a carbon, there's a carbon here, there's a carbon here. There's 3 protons here, but there is a two protons here, which is bonded to a CH3. So we'll give precedence to this ethyl group over the CH3. So the CH3 becomes the third. And then the deuterium is the 4th. And we've said that the least group must be facing away from you, must be pointing away from you. And in this case, the deuterium is the least group, and it is on the dash bond. That means it is pointing away from us. So we cover the least group, and then we check the rotation. So it becomes 1, 2, 3. This is anti-clockwise direction, and therefore this is an S configuration. What is the configuration of this molecule? So first, oxygen becomes number 1, and then second, you can see that this is a CH2. However, this is a CH. If we were to expand this side, it will look like this. A C bonded to a proton, that is bonded to a CH3, a CH3. So you can see that, and then bonded to the, you can see that this looks more or less like an isopropyl group. So here's a CH2, however, here's a CH bonded to a carbon. So we'll give precedence to this group over this group. So this becomes 2, and this becomes 3. And then the proton becomes number 4. And we said the number 4 must be on the dash bond, the bond pointing away from us. And then we'll cover that group. So if we cover the group, you can see that it is 1, 2, 3. And that is going in the anti-clockwise direction. So this configuration is an S configuration. What is the configuration of this molecule? So let's assign priority. In assigning priority, you can see that this is a CH2 group. However, if you come here, you can see that this is a CH group. It's bonded to 1 carbon here and another carbon here. But this is bonded to 2 protons. So we will give precedence to this group, number 1, over this group, proper group. Sorry, a butyl group. This is number 2. And we give precedence to a butyl group over an ethyl group. So the ethyl group becomes number 3. And then the CH3 group becomes number 4. And we said that the least group must be pointing away from us. The CH3 is pointing away from us. So we will cover that CH3 and we will determine the direction in which it is moving. So it is moving from 1 to 2 to 3. It's moving in the anti-clockwise direction. And therefore, this is also an S configuration. Now, what is the configuration over here? You see that if you look here, the only chiral center is this carbon, because this is a carbon doubly bonded to an oxygen. So this is not a chiral center. Now, this carbon is bonded to an OH group. We'll give precedence to the OH group. So the OH group becomes number 1. Then this is bonded to a carbon. Now, this carbon is doubly bonded to a proton. However, this carbon is doubly bonded to an oxygen. So we'll give precedence to this double bonded carbon doubly bonded to an oxygen than a carbon bonded to a proton, because an oxygen has a higher molar mass than a proton. So this becomes number 2, and this becomes number 3, and then the proton becomes number 4. We said that the least group must be pointing away from us, so it must be on the dash bond, and it is just exactly like that in this situation. So you cover the least group and you determine the direction in which it is rotating. So if we cover the least group, this becomes 1, 2, 3 in the anti-clockwise direction. So this is also an S configuration. What is the configuration in this case? You can see that the difference between this and what we've done previously is that in this case, the least group is pointing directly towards us. In all the previous examples, the least group was pointing away from us. So let's assign priority. The fluorine is number 1, the ethyl is number 2, and then the CH3 is number 3, and the proton is number 4. If the least group is pointing towards us and not pointing away from us, what we must do is to still assign the configuration and then negate the configuration at the end. So if it is an S, we'll negate it to an R, and if it is an R, we'll negate it to an S. So let's cover the least group in this case. If we cover the least group, here becomes 1, 2, 3. So if we cover the least group, it is moving in this direction, which is an R. However, because the least group is pointing towards us and not pointing away from us, we'll negate the configuration, and therefore this is an S configuration. What is the configuration in this case? So the oxygen is number 1, then the ethyl group is number 2, then the methyl group is number 3, and the proton is number 4. So in this case too, the least group is pointing towards us. It's not pointing away from us. So we'll still have to do the configuration and negate it at the end. So it's going to be 1, 2, 3 when we cover the least group. And this configuration is an R. It's going in the clockwise direction, which is an R. However, because the least group is pointing towards us, we will negate it, and this is an S configuration. Let's determine the configuration of this molecule as well. In assigning group, this is an oxygen. Oxygen has a higher molar mass than a carbon. So this is 1. Then we have a carbon that is doubly bonded, that is bonded to 2 CH3 groups. And here Because there is a double bond here, we must look at this carbon as two carbons, but this is one carbon, and therefore here is number 2, and then this is number 3, and then the deuterium, the D is deuterium, is number 4. So the least group is not pointing away from us, but it is pointing towards us. If we cover this, you will see that this is 1, 2, 3. 1, 2, 3 is going in the anti-clockwise direction, so it's an S. However, because the least group is pointing towards us and not pointing away from us, we will negate this configuration, and therefore this configuration is an R configuration. Now let's look at this situation as well. So let's assign priority. This is 1 because bromine has a higher molar mass than on oxygen. This is an OH, but this is a CH3. We give precedence to the CH3 than the OH. And therefore, this is number 2. And then this OH is number 3. And this is number 4. But you can see that the least group here is neither at pointing towards us nor pointing away from us. And this is different from the 2 situations we've looked at in the previous examples. So in the situation where the least group is neither pointing towards us or pointing away from us, what you will do is that you will swap the groups. That is, you will swap the group that is pointing away with the least group. So in this case, the group that is pointing away is the OH group. So we will swap it with the least group. So here becomes 3. And this becomes 4. And then when we are done with swapping the 2, then we'll swap the other 2. So in this case, the 1 becomes 2, and then the 2 becomes 1. And therefore, the new arrangement is 1, 2, and then 3. And then this is 4. So if we cover the least group, it is 1, 2, 3. And 1, 2, 3, it is going in the S direction. And therefore, this molecule is an S. So let's assign configuration in this situation as well. We have a sulfur group here, and then we have an oxygen group. Sulfur has a higher molar mass than oxygen, and therefore the sulfur becomes number 1. Then followed by the oxygen, which becomes number 2. Now with this group, there's a CH, there's a proton here, and then there's also a proton here. So there's a CH here bonded to a chlorine, and this is a CH bonded to another CH3. So this group will come first before this group. So this becomes number 3, and this group becomes number 4. But you can see that number 4 is neither pointing towards us nor pointing away from us. So the rule says that we should swap the number 4 with the group that is pointing away from us. And when we do the swapping, we will also swap the other 2. So we are going to swap 4 and 2 because 2 is the group that is pointing away from us. So this side becomes number 2, and this side becomes number 4. So we have to swap this other 2. So this becomes number 1, and this becomes number 3. So if we cover here, you can see that this is 1, 2, 3. And 1, 2, 3 is going in the clockwise direction. And therefore, this configuration is an R configuration. What is the configuration here? You can pause the video at this point and try. So this is a fluorine group. Fluorine has a higher molar mass than a carbon. And the fluorine becomes number 1. Then because this carbon is a double bond carbon, it becomes number 2. And this is number 3. And this is number 4. In this case too, the least group is neither pointing towards us nor pointing away from us. And therefore we need to swap. The group that is pointing away from us is the fluorine group. So we need to swap number 4 with number 1. and therefore here becomes number 4 and here becomes number 1. If we swap these two, then we must also swap these two. Therefore here becomes number 3 and here becomes number 2. So we need to cover the least group. If we cover that, we are left with 1, 2, 3. 1, 2, 3 is an R, so it is moving in the clockwise direction. Therefore, this is R configuration. What is the configuration in this case? So let's assign priority. Oxygen becomes number 1. And then this is a double bond, so the number bond becomes number 2. And then this becomes number 3 and this is number 4. However, the least group is neither pointing towards us nor away from us. So it is inside the plane of the molecule. And we need to swap its position with the group pointing away from us, which is the weight group. And therefore, here becomes number 1 and this becomes number 4. If we are done, then we'll swap the other two. So here becomes number 3 and here becomes number 4. So we'll cover the least group. If we cover the least group, you see that this is 1, 3, 4. So it is going in the anti-clockwise direction. Sorry, I made a mistake. So if we swap these two, then here becomes number 3 and here becomes number 2. Sorry for that mistake. So therefore, if we cover the least group, it's going to give us 1, 2, 3. 1, 2, 3 is in the clockwise direction, and therefore this configuration is also an R configuration. Let's determine the configuration in this situation. Which one becomes first? Nitrogen has the highest molar mass among this, so nitrogen becomes number 1. And then you can see that this CH2, this is CH2, this is CH3. This carbon is bonded to an arene group, so it becomes number 2. And then here becomes number 3. This is a proton. And the proton becomes number 4. Since the proton is already pointing away from us, if we cover that part, we are going to get 1, 2, 3. So this is an S, anti-clockwise direction. Will this molecule be optically active? Why do you think it will be optically active or optically inactive? So what we need to do is to determine if this molecule has a chiral center. If we come here, so there's a proton that is pointing away from us in this case, and there's also a proton pointing away from us in this case. Now, is this a chiral center? We need to check from this carbon and this carbon. You can see that this is CH2 and this also is CH2. So because we have two groups that are the same, this is not a chiral center. You can see that this one too is bonded to an H, a CH2 and a CH2. CH2 and CH2 are the same. And therefore, this is not also a chiral center. Let's assume that we had a bromo group and a chloro group at these two carbon, at these positions. You see that in that case, this carbon becomes a chiral center because we have a CH3 group here. Then we have a CHBr group in this case. And then in this case, we have a CHCl group and then a proton here. So because we have 4 different groups that are bonded to this carbon is a chiral compound. Let's determine the configuration in this case. So proton is already pointing away from us. This is CH3. Bromine has a higher molar mass than the chlorine group. So this part becomes 1. And this is number 2 and then number 3. If we cover number 4 is the proton. If we cover it, then 1, 2, 3 is going in the anti-clockwise direction, and that is an S configuration. This is also a chiral center. So let's determine the configuration in this case. So This is still number 1, number 2, and here's number 3. The proton number 4 is already pointing away from us, and if we cover it, it is 1, 2, 3, and that is in the clockwise direction. This is an R. So you see that at one side of this molecule we have an S configuration, and then at the other side is an R configuration. The S and the R will cancel out, and therefore this molecule is an optically inactive molecule, even though it has chiral centers. And this is because you can see that if we stand here, there is a plane of symmetry around these carbons. So this group and this group, they are the same. So because of this plane of symmetry in this compound, it makes the compound optically inactive, even though it has chiral centers. Those kind of molecules that have plane of symmetry in them, even though they have chiral centers, are called the meso compounds.